Good afternoon. In yesterday's lecture, we had discussed tree data structure. Then we had discussed binary tree. First, we have discussed generalized tree, then binary tree, binary search tree, and AVL tree. Now, today we'll continue with B tree. So, B tree is a specialized M-way tree that can be widely used for disk access. First of all, what is B tree? So, B is for balanced. It is a balanced tree. It is a specialized M-way tree. Means we can have binary tree which is having two childrens. Here it is a specialized M-way tree, and it is basically used for disk access. Now, what exactly disk access is? So whatever data is there, we cannot store that data in main memory. We have to store that data in secondary memory, that is in your hard disk, because the bulk data we cannot store it in main memory. But whenever we are going to store data in the secondary memory, we have to keep record of that where we have stored the data. So for that we have to prepare index. Now that index is that index is having key and the record pointer pointing towards the record where we have stored the data. So for storing that index, we use this B tree data structure. Now, what exactly will be there in B tree? In B tree, we'll be having two things. One is the key, and second is the record pointer, which is pointing towards the record where exactly we have stored it. So that we don't have to search the whole hard disk every time we want to get any data from there. If I have stored 5,000 records and I want some random record from there, from the hard disk, so I have to search all the 5,000 records. It may happen that I'll get that record in first attempt only, but it may happen that somewhere in between that record is kept, so I have to wait for that much amount of time for searching that record. So instead of that, instead of accessing the whole disk, what we are doing is we are storing one index, and in that index we are storing some key information with the help of which we can search data. For example, if we have to search data about students, so we can do it with the help of enrollment number or the registration number, because roll number is not the unique thing with which we can identify the students, because every class is having same roll number. So instead of that, either your enrollment number or your registration number, that will be unique. Every student will get one registration number, so that registration number can be a key, and with the help of this key we can find out, okay, we want to search this particular data. So in the B tree we are going to find it, search it. That B tree will be small, that data structure, that index will be small as compared to the actual data. So there we'll be having a record pointer which is pointing towards that record. Actually, if I want a student's record, so I'll search it with the registration number, and the memory location I'll get that here exactly the data of this particular student is stored. So I'll get that detailed data of that student in secondary memory. So for making that accessing fast, we are using this B tree data structure, and this B tree is basically used for storing index. So a B tree of order M. Now what exactly order M means? How many number of, for example, a B tree of order M can have at most M minus 1 keys and M children. So this order of the tree is very important. This will tell us that in one node how many number of keys we can store and how many number of childrens will be there of root node. So as the name says, it is a balanced tree, so we have to balance the leaf nodes. Apart from that, we have to see first of all how many children will be there from one node, how many children can be there. So from one node, if the order of the tree is m, so from one node we can have 5 m children. For example, if the number is 5, that order is 5. A B tree is of order 5. So this means that in one node we can have at most 5 minus 1, that is 4 keys, and 5 children. So this order of the tree is very important. Then one of the main reason of using B tree is its capability to store large number of keys in a single node and large key values by keeping the height of the tree relatively small. So why we are not using AVL tree, why we are not using a binary search tree or B tree? Because in there the disadvantage is that in one record we can store only one value. In one node we can store only one value, whereas here in B tree in one node we can store multiple values. Now how many values we can store? It depends upon the order. So if the order is m, so we can store m minus 1 keys in one node. So that is one advantage or main reason of using this B tree is that multiple values can be stored in one location. Plus, because of this, since we can store large key values, so height of the tree will be relatively small, so searching will become more efficient. A B tree of order m contains all the properties of an M-way tree. In addition, it contains the following properties. So every node in a B tree contains at most m children. The order of the tree is m and every node can have m children. So that is the point. Every node in a B tree contains at most m children. We have to strictly follow this. Because of this only we can say that all the leaf nodes will be on one level. Every node in a B tree except the root node and the leaf node contain at least m by 2 children. So this is important. If order of your tree is 5, so 5 by 2, that will give you 2.5. So either you can take 3 or you can take 2. So that is minimum. Maximum you can have 5 children. If the order of the tree is 5, you can have 5 children. But minimum you can have at least 2 children. You must have at least 2 children. Then only your tree will be balanced. The root nodes must have at least 2 nodes. All leaf nodes must be at the same level. So these are the properties of B tree we have to follow whenever we are going to insert a new node. Every time we have to see that we are not violating the properties. Like in AVL tree, every time whenever insertion or deletion is there, we used to calculate the balance factor, and depending upon the balance factor, we used to balance the tree. We used to perform the rotations and we again balance the tree. Same way here, whenever we are inserting a node or deleting a node, we have to take care of this, that we are not violating the properties of B tree. Now this is the example for B tree. So here you can see root node is there. This is of order 3. This B tree is of order 3. How we have guessed that this is of order 3? Because you can see maximum we are having 3 children. A node can have 3 children. So 3 with this we can say that okay, we are having order 3. How many number of keys we can have? 3 minus 1, that is 2. So every node will have 2 keys except the root node. Rest of the nodes will have 2 keys. Maximum 2, minimum it can be 1. So that's why in root node you can see we are having only 1 key. So this is the structure, and this is somewhat different from the normal structure. In normal structures, in normal BST or B tree, binary tree or BST or AVL tree, at one location we can store only one element. Here we can store multiple elements. Now the operations which we can perform on B tree. So first is searching. So searching in B trees is similar to that in binary search tree. For example, if we search for an item 49 in the following B tree, the process will something like following. So for example, if this is the tree and we want to search 49, so first we'll see 78, 49 is less than 78, so we'll come to left. 40 is greater than say 49, so we'll go to right, that is 56. 49 is less than 56, so we'll go to left, that is 45. 49 is greater than 45, so now we'll get 49. So in this way, like similar like BST, we are searching here. So compare item 49 with root node 78. Since 49 is less than 78, move to its left subtree. 49 is in between 40 and 56, traverse the right subtree of 40. Then 49 is greater than 45, move to right. Compare 49, match found. In this way, searching is done. Searching in a B tree depends upon the height of the tree. The search algorithm takes O of log n time to search any element in a B tree. So this is very important. Searching time is quite less as compared to other trees. Now next, the other operation, insertion. So insertions are done at the leaf node level. Once we had created the tree, now if we want to insert any node in between, so insertion can be done at the leaf nodes. We have to follow the given algorithm for that. So the algorithm says traverse the B tree in order to find the appropriate leaf node at which the node can be inserted. So first of all, we have to find out the position where we have to insert the node. Now, if the leaf node contains less than m minus 1 keys, then insert the element in the increasing order. So in a node, we can have m minus 1 keys only. For example, if the tree's order is 5, we can have 4 keys in a leaf node. Now, if a leaf node is having less than 4 keys, then we can insert this new key here in the order. We have to follow the order. And if this is not the case, if the leaf node already contains m minus 1 keys, then follow the following steps. If the leaf node is already having 4 keys, we cannot insert the fifth one. So then we have to follow the further steps. Insert the new element in the increasing order of elements. So here the solution is, you are already having 4 keys, insert the fifth key also in the increasing order of elements. Now after inserting, it will violate the property, because if the order of the tree is 5, there must be 4 keys. Right now we are having 5 keys. So now split the node into the 2 nodes at the median. Find out the median, and from median split the node into 2 nodes. Now push the median element up to its parent node. And if the parent node also contains m minus 1 number of keys, then split it 2 by following the same steps. ये कहाँ तक करते जाना है? We have to repeat this step up to root. So in this way, we have to do the insertion thing. So we'll see this with the help of example. Insert the node 8 into the B tree of order 5 shown in the following image. So we have to insert node 8. So first of all, we have to find the location where exactly we have to insert 8. So 8 is less than 60. We'll traverse to left. 8 is less than 29. Again, we'll go to left. Now in the left, we are having elements. 8 is greater than 3. We have to move to right. 8 is greater than 5. Again, we'll move to right. 10 is less than 8 is less than 10. Then we have to insert 8 in between 5 and 10. That is for sure. Now the thing is, this tree or this leaf node is already having 4 keys. Whereas the rule says if order of the tree is 5, you can have maximum 4 keys. So now this is the situation where we have to divide or split the leaf node. So for that, first we have to do the insertion thing. So first of all, we'll insert 8 in between 5 and 10. So here you can see we have inserted 8 in between 5 and 10. After insertion, now we'll find the median node and we'll push that median node to its parent node. So the median node here is 8. So we have to push 8 upwards and we have to split this particular leaf node into 2. So here you can see 3, 5. Since 3 and 5 are less than 8, so they'll be on the left of 8. And 10 and 23 is greater than 8, so they'll be on the right of. So in this way now, in the leaf node, we are in the parent node, we are having 8, 29 and 32. So what we had done, we had splitted this leaf node into 2 और एक नोड हमने ऊपर पेरेंट नोड की तरफ शिफ्ट कर दिया है. Next is deletion. Deletion is also done in the same way. Again, deletion is also performed at the leaf nodes. The node which is to be deleted can either be a leaf node or an internal node. Following algorithms needs to be followed in order to delete a node from a B tree. First of all, locate the leaf node which we have to delete. If there are more than m by 2 keys in the leaf node, then delete the desired key from the node. Now we have to see minimum nodes conditions. Now if there are more than m by 2 keys, so for example, order of our tree is 5. 5 by 2 is, if we are taking on lower side, 5 by 2, it will give us 2. So minimum 2 leaf nodes should be there, or 2 keys should be there. Now if there are more than m by 2 keys, then there's no problem. आप leaf node उस key को delete कर दीजिए, you'll have the node there only. But if the leaf node doesn't contain m by 2 keys, then complete the keys by taking the element from left or right sibling. So what we have to do after deletion, if we violate the property of B tree, we have to take either from left or either from right. Now, from where exactly we have to take the node or key? So, if the left sibling contains more than m by 2 elements, then push its largest element up to its parent and move the intervening element down to the node where the key is deleted. So, what you have to do is, if if the left sibling contains more than m by 2 elements, then its largest element should be pushed to the parent node, and remaining nodes will be merged with the deleted key one. So in this way, left, in this way we have to follow the process for right as well. If neither of the sibling contain more than m by 2 elements, then create a new leaf node by joining two leaf nodes and the intervening element of the parent node. If neither the left child and nor the right child will have more than m by 2 elements, then what we have to do is we have to join these elements, and we have to जो भी इनमें जो सबसे बड़ा element हो, we have to join these two nodes, और इनमें से जो सबसे बड़ा element होगा we have to push that element to the parent. If parent is left with less than m by 2 nodes, then apply the above process on the parent too. In this way, recursively, we have to repeat the process up to root. So in this example, delete the node 53 from the B tree. So first of all, we have to find where is 53. So 53 is less than 90. We'll go to left. 53 is greater than 49, and 53 is less than 60. So in between we'll get 53. So now we have got 53 and 57. After deleting 53, 57 will be left alone. So first of all, we'll delete 53. After deleting 53, 57 will be the only element there, and that is not that is against the property of B tree. So what we'll do, we'll bring 49 down, because we cannot merge 57 with 34, because if we'll merge 57 with 34, we are violating the property of B tree. Because 57 is greater than 49, so we cannot put it to the left. So what we'll do, we'll bring 49 down and we'll add 57 with it. So here you can see 49 came down, and now we have added 57 with it. Now the property is maintained. Now 57 is the only element which is left in the node. The minimum number of elements that must be present in a B tree of order 5 is 2. It is less than that. The elements in its left and right subtree are also not sufficient. Therefore, merge it with the left sibling and intervening element of parent, that is 49. So we have brought 49 down, and now we have added 57 to that, and we have created one new node. So in this way, deletion is done in B tree. Now next is B plus tree. So this is also a B tree, but with some different features. So this is more advanced tree. So after studying B plus tree, we'll see the difference between B tree and B plus tree, because function of both the trees are same. Like both the trees are used for storing index, but the way in which the index values are stored, that is different. It is more efficient in B plus tree. So B plus tree is an extension of B tree which allows efficient insertion, deletion and search operations. So as compared to B tree, B plus tree is more efficient while performing insertion, deletion and searching operations. And these three operations are important. On a tree, we are performing these three operations only. In B tree, keys and records both can be stored in the internal as well as leaf nodes. Keys and records both can be stored in the internal as well as leaf nodes, whereas in B plus tree, records can only be stored on the leaf nodes, while internal nodes can only store the key values. In B plus tree, records can only be stored on the leaf nodes, while internal nodes can only store the key values. This means what? That the leaf nodes will have key values as well as records, whereas the internal nodes will have only key values. The leaf nodes of a B plus tree are linked together in the form of a singly linked list to make the search queries more efficient. Because of this advantage that we have to store keys as well as records on leaf nodes only, Now all the records or data are at the same level, that is at leaf node. Now while searching, we have to search the leaf nodes only. We don't have to search the internal or intermediate nodes. So with the help of that, searching becomes more efficient here. The nodes of a B plus tree are linked together in the form of a singly linked list. So this will make searching more efficient. Here you can see in the diagram, in the last line, you can see all the leaf nodes are at the same level, plus the leaf nodes are linked together like a linked list. So this will make searching more efficient. B plus tree are used to store the large amount of data which may not be stored in the main memory. This is the same thing that if always we used to store the data in hard disk, and where exactly we had stored that data on hard disk, that we used to store in this data structure tree that is called as index. So indexing is done here. So now we cannot keep, so it is very difficult to keep that index, full index, in main memory. So what we can do is we can divide this and we can keep some portion of it in main memory and some portion of it in secondary memory. So B plus tree are used to store the large amount of data which may not be stored in the main memory. Due to the fact that size of main memory is always limited, the internal nodes of the B plus tree are stored in the main memory, whereas leaf nodes are stored in the secondary memory. So what we are saying, that a single data structure is stored in two different memories. So the leaf nodes can be stored in the secondary memory and the intermediate or internal nodes can be stored in main memory. This is the advantage. The internal nodes of B plus tree are often called as index nodes. This is the index a B plus tree of order 3. B plus tree of order 3 means a node can have three, at max 3 children. So you can see in node, intermediate nodes are having 3 nodes, 3 child nodes. Then if order is 3, then maximum we can have 3 minus 1. That is 2 number of keys. So here you can see in every leaf node we are having 2 number of keys. Now what are the advantages of B plus tree? So records can be fetched in equal number of disk accesses. So in less number of disk accesses, we can fetch the record. Height of the tree remains balanced and less as compared to B tree. So as compared to B tree, height of the B plus tree is less. We can access the data stored in a B plus tree sequentially as well as directly because of the links. Because of the links, we can directly access the data stored here. Keys are used for indexing. Faster search queries as the data is stored only on the leaf nodes. Now, insertion in B plus tree. So, first of all, we have to locate the location where we have to insert. Then insert the new node as a leaf node. If the leaf doesn't have required space, split the node and copy the middle node to the next index node. If the index node doesn't have required space, split the node and copy the middle element to the next index page, and so on. So here you can see we have to insert value 195. The tree is of order 5. Order of the tree is very important. So the order of the tree is 5 and we have to insert 195. So 195 is greater than 120. So we'll directly come to right of 120. So here we are having 129, 154, 190 and 200. 200 is not displayed in the diagram, but we are having 200 there. So already we are having 129, 154, 190 and 200. 4 elements are already there, 4 key values are already there, and the order of the tree is 5. So at max we can have 4 keys. So first we'll insert 198 and then we'll see what exactly we have to do. So first we'll insert 198. So it is between 190 and 200. We'll insert 190. Sorry, 195 is we have to insert. So we'll insert 195 here. Now after inserting 195, we'll find the median. Median is 190. So what we'll do, we'll push 190 to root node and we'll divide that node into two: 129, 154, 195 and 200. So what we had done, we are having five key values in a node. So we cannot do that because it is violating the property of b plus 3. So what we'll do, we'll find the median. Median is 190. We'll push that 190 to the parent node and we'll split this node into two, and now 129 and 154 will be in one node and 195 and 200 will be in another node. Now the thing is, the root node is violating the property because again it is having five key values in it. So what we have to do is, we have to find out the median. Median is 108. 108 will become the root node, and again we'll divide this node into two. One is 60, 78, 120 and 190. So here you can see 108 will go up, 60, 78, 120 and 190. So in this way, insertion is done in B plus tree. Next is deletion in B plus tree. So delete the key and data from the leaves. Again, deletion is possible only through leaves. If the leaf node contains less than minimum number of elements, merge down the node with its sibling and delete the key in between them. If the index node contains less than minimum number of elements, merge the node with a sibling and move down the key in between them. For example, we have to delete 200. Now, after deleting 200, we'll have 195. After deletion, 129, 154, there we are having 195 and 200, and we have to delete 200. So only 195 will be left. So what we can do is, we can merge that 195 with 154. So here you can see, हमने 190 को नीचे लाया, 129, 154, 190 को हमने नीचे लाया, and then we had inserted 195 there. So after deletion, what we had done, we had merged two nodes. Now the point is, 120, जो parent node है वहां पर 120 is alone, so we have to merge it. So what we can do is 60, 78, 108 and 120. We'll merge it. So here after merging, you can see one parent node and rest of the child nodes are there. Now we'll discuss one more topic, that is difference between B tree and B plus tree. So search keys cannot be repeatedly stored in B plus trees, whereas in B plus trees redundant search keys can be present because of the advantage that the keys will only be on the leaf node. The record will only be there in the leaf node. That's because of this advantage. We can store redundant search keys in B plus tree, whereas this is not possible in B tree. In B tree, data can be stored in leaf nodes as well as internal nodes, whereas in B plus tree, data can only be stored on the leaf nodes. Searching is slower in B tree as compared to B plus tree. Deletion of nodes or internal nodes are complicated in B tree as compared to B plus trees. In B trees, leaf nodes cannot be linked together, whereas in B plus trees, leaf nodes are linked together. So that's why B plus tree is more advantageous than B tree. Now next we'll look into the problems. So a binary tree T has n leaf nodes. The number of nodes of degree 2 in T is, so the question is related to binary tree. So a binary tree has n leaf nodes. So the number of nodes of degree 2 in T is, the question is how many number of nodes will be there. Those are having degree 2, means those are having two childs in it. A binary tree is there which is having n leaf nodes. The question says how many number of nodes will be there. those who are having degree 2, means those who are having 2 childs. So it is n minus 1. A binary tree is a tree data structure in which each node has at most 2 child nodes. The number of subtrees of a node is called the degree of the node. In a binary tree, all nodes have degree 0, 1 or 2. The degree of a tree is the maximum degree of a node in the tree. So a binary tree is of degree 2. So usually a binary tree is of degree 2. So you can say if we are having n leaf nodes. For example, if we are having 4 leaf nodes. So the number of nodes of degree 2, how many number of nodes will be there? Those who are having degree 2. So it is n minus 1. N minus 1 means 3. So if you are having 4 leaf nodes, then in that tree, you can have 3 nodes whose degree is 2. In the balanced binary tree, how many nodes will become unbalanced when a node is inserted as a child of G? I'm sorry for this, there's no picture. There's one diagram which is given to us, which is not here. In the balanced binary tree in the figure given below, how many nodes will become unbalanced when a node is inserted as a child of the node G? So in a balanced binary tree means in an aerial tree. So when if we going to insert any node, we have to calculate the balance factor, and while calculating balance factor we have to see that how many nodes are getting imbalanced. So I'm really sorry for this, there's no tree diagram here. With the help of that tree diagram I can easily tell you that how many nodes will get imbalanced. Here we have to traverse the same tree in post order traversal, and then we have to tell the correct option, like this is the post order traversal of that particular tree only. Next problem. A binary search tree is generated by inserting in order the following integers. The number of nodes in the left subtree and right subtree of the root respectively is. So here what we have to do is we have to create a binary search tree by inserting the nodes in the order in which it is given. So 50 is the first node, so 50 will become the root node. Here you can see 50 will become the root node. After 50 it's 15, so 15 is less than 50, so 15 will be in left of 50. So here you can see 15 will be in left of 50. Then next is 62. 62 is greater than 50, so it will come in the right of 50. So that is 62. After 62, it's 5. So we'll compare 5 with 50. 5 is less than 50. Then we'll go to left. Then we'll compare 5 with 15. 5 is less than 15. Again, we'll go to left and we'll insert that node there. After 5, it's 20. So we'll compare 20 with 50. 20 is less than 50. So we'll move towards left. 20 is greater than 15. So we'll move towards right and we'll insert this node there. After 20, it's 58. So 58 is greater than 50 and it is less than 62. So we'll insert 58. Then 91. So 91 is greater than 62. So we'll insert 91 in the right of 62. Then 3, 8, 37, 60, and 24. So in this way, we'll search, we'll first compare the node with the root node, then we'll decide where we have to move further left or right. Then again, we have to do this, and after finding the correct position, we have to insert that particular node. So in this way, a binary search tree is created. Now the question is, how many nodes are there in the left subtree and how many nodes are there in the right subtree? So in left subtree, 1, 2, 3, 4, 5, 6, 7, 7 nodes are there, and in right subtree 4 nodes are there. So the correct option is B, 7 and 4. 7 nodes in left subtree and 4 nodes in right subtree. A binary search tree contains the value 1, 2, 3, 4, 5, 6, 7, 8. This is in order. The tree is traversed in pre-order and the values are printed out. Which of the following sequences is a valid output? So first of all, we have to draw the tree. Considering the pre-order traversal, we have to construct the binary search tree. Now after constructing it, we have to traverse it in order. Then only we can say that, okay, this is the thing. So first we have to construct the tree, and then we have to traverse it in order. In order is given to us, pre-orders are given to us, but we don't know which option is correct. So we have to draw the tree for for all the four options, and finally we can conclude that correct tree we'll get after performing the same for option D. A complete n-ary tree is one in which every node has 0 or n sons, or n childs, you can say. If x is the number of internal nodes of a complete n-ary tree, the number of leaves in it is given by x into n minus 1 plus 1. So the correct option is x into n minus 1 plus 1. The solution for that is given to us. The question is, a complete n-ary tree is one in which every node has 0 or n sense. If x is the number of internal nodes, the number of how many number of leaves will it will be having? So here, leaf nodes and intermediate nodes. So here the calculation for that is given to us, that with one internal node, we are having n leaf nodes. If we are having two internal nodes, we are having 2 into n minus 1 leaf nodes. If we are having three internal nodes, 3 into n minus 2 leaf nodes. If it is x internal node, then it is x into n minus 1 plus 1 leaf nodes. Consider the following nested representation of binary trees. XYZ indicates Y and Z are the left and right subtrees respectively of node X. X, Y and Z. So X is root, Y is left and Z is right subtree of node X. Note that Y and Z may be null or further nested. Now which of the following represents a valid binary tree? In that same form. So first option is not correct because a node can have three nodes only. So it is 4, 5, 6, 7. So that is not in proper structure. Then option B is also not correct. Option C is the correct option. So option A is not possible because the right subtree 4, 5, 6, 7 is not in the correct format. Option B is not possible because 2, 3, 4 cannot be the root of left subtree of 1. Option D is not possible because 4, 5 is not in the correct format. 4's right child is not specified. If it was 1, 2, 3, 4 null, 4, 5 null, then it will be valid, but that is not the option. So the correct order is 1, 2, 3, 4 and 5, 6, 7. 1 will be the root node, 2, 3, 4 will be the left subtree, and 5, 6, 7 will be the right subtree. Again, 2 will be the node. After 1, 2 will be the node. After 2, 3 and 4 will be its child. Similarly, 1 के right में 5 आएगा, 5 के left में 6 और 6 के 5 के right में 7. In this way, जो हमको दिया हुआ है structure, root, left, right. So here you can see this is root, this is left tree and this is right tree. In that also, this is root, this is x, this is y, this is z. Again this is x, this is y, this is z. Here this is x, ये जो 2, 3, 4 है ये y हो गया और 5, 6, 7 जो है वो z हो गया. So इस फॉर्मेट में सिर्फ ऑप्शन सी ही सही आता है. The most appropriate matching for the following pairs: x and x, y, z and 1, 2, 3. We have to match these pairs. So x is depth first search. So we have to see what data structure will be suitable for depth first search. So for depth first search, stack is there. For breadth first search, queue is there. And for sorting, it's heap. So correct option is option C. Stack is used for depth first search, queue is used for breadth first search, and heaps are used for sorting algorithms. Let last post, last in, and last pre denote the last vertex visited in post order, in order, and pre order traversal. These three are basically variables: last post, last in, and last pre. These denotes the last vertex visited in a post order, in order, and pre order traversal. So, for example, if this is a tree A, B, C, D, E, F, we have to find out pre order, in order, and post order of it. So, pre order of this tree is given, not given, we have to find out pre order of the tree. Pre order means root first. Then we have to traverse in order and then post order. In post order, root will be last. Now we are having three variables: last post, last in, and last pre. And what is there in these three variables? The last node visited in post order, in order, and pre order. So last post is equals to A. In post order, you can see the last vertex visited is A. So last post is equals to A, last pre is equals to F, and last in is equals to C. So it is A, F, and C. And here the option says last in is equals to last post, last in is equals to last pre, and last pre is equals to last post. And the correct option is none of the above, because last in is C and last post is A. So C is equals to A? No. So in this way, the correct option is D. Suppose the numbers are inserted in that order into an initially empty binary search tree. The binary search tree uses the usual ordering on natural numbers. What is the in order traversal sequence of the resultant tree? So first of all, the numbers are given to us, and in this way these numbers are inserted in a tree, binary search tree. Now we have to read that binary tree into in order. So usually in order we get the data in sequence. So here you can see option C, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We are getting it in order. So the correct option is option C. So the tree which is given to us, like 7. So after 7 we have to insert 5. So 5 will be on left. After 5 we have to insert 1. So 1 will be on left. Then 8. So 8 will be there after 7, right of 7. Then 3. 3 will be there on right of 1. Then 6. 6 will be there on right of 5. Then 0. 0 will be there left of 1, and so on. In this way we have to draw the tree first, and then we have to traverse it in order. So in order traversal will give us the sequence in order. So it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So correct option is C. The following numbers are inserted into an empty binary search tree in the given order. What is the height of the binary search tree? So first we have to insert 10. So 10 will be the root node. Then 1 will go to left. 3 3 will go to right of 1. 5 will go to right of 3. 15 will go to right of 15, 10, and so on. So first we have to draw the tree. So we had drawn the binary search tree, and now we have to find height of it. So height of binary search tree is 3. This particular binary search tree is 3. So the correct option is option B. The maximum number of binary trees that can be formed with 3 unlabeled nodes is, the correct option is 5. But here you can see how many number of binary trees can be formed with 3 unlabeled nodes. So you can see the combination, we can draw 5 different combinations of binary trees. So the correct option is B, that is 5. The in-order and pre-order traversal of a binary tree are respectively. The post-order traversal of the binary tree is. So what we have to do is the in order and pre-order traversals are given to us. By looking to in order and pre-order traversal, we have to draw the tree, and then we have to traverse it in post order, and then we have to compare it with the options which are given to us. So first we'll draw the tree. So the tree is drawn here, like in order, and pre-order is given to us. So with this we can conclude that A is the root node. From pre-order, the first node is the root node, so from that we can conclude that A is the root node. Now in order, you can see DBE is in left of A and FCG is on right of A. So we can draw in this way that DBE will come to left of A and FCG will come to right of A. In this way we have to draw the tree. Now after drawing the tree, we have to traverse it in post order. After traversing it in post order, we have to compare it with the options which are given to us, and the correct option is A. Post order traversal of a given binary search tree produces the following sequence of keys. This is the post order traversal which is given to us. Which one of the following sequences of keys can be the result of an in order traversal? So this is very simple. If one of the traversal is given to us, we have to find the another traversal. So usually in order traversal, we get the data in sequence, in increasing order. So here in increasing order, we are getting the data in option A: 9, 10, 15, 22, 23, 25, 27, 29, 40, 50, 60, and 95. This is sorted and in order. So the correct option is option A. Which one of the following is a key factor for preferring B trees to binary search trees for indexing database relations? So we have to find out which option is suitable or correct for preferring B trees over BS tree, binary search trees. So option A says database relations have a large number of records. Database relations are sorted on the primary key. B trees requires less memory than binary search trees, or data transfer from form disks is in blocks. So the correct option is D. The B tree is a generalization of a binary search tree. In B tree, a node can have more than 2 children. All the properties of the B tree are discussed here, and with this we can conclude that the correct option is option D. What is the maximum height of any AVL tree with 7 nodes? Assume that the height of a tree with a single node is 0. Maximum height of any AVL tree with 7 nodes. So here you can see we had drawn two options here, option 1 and option 2, and in both the height of the tree is 3. So the correct option is option B. A binary tree T has 20 leaves. The number of nodes in T having 2 children is, so it is, if we are having n number of leaf nodes, then the number of nodes of degree 2 is n minus 1. So if we are having 20 leaves, we can have 19 two children nodes here. So the correct answer is 19. The post-order traversal of a binary tree is given to us. The in-order traversal of the same tree is again given to us. The height of a tree is the length of the longest path from the root to any leaf. The height of the binary tree above is. So what we have to do is we have to draw the binary tree with the help of this post-order and in-order traversals. After drawing the binary tree, we can conclude that what is the height of the tree. In this example, the height of the tree is 4. Here you can see the post order and in order traversals are given to us. From that we have to construct a binary tree, and from that we have to find out the height of the binary tree. Which one of the following statements is not correct about the B plus tree data structure used for creating an index of a relational database table? So B plus tree is a height balance tree. It is correct. Non-leaf nodes have pointers to data records. B plus tree. So the B plus tree doesn't have data records in non-leaf nodes. Data records are there only in leaf nodes. So the second option is incorrect. Key values in each node are kept in sorted order. So this is true. Each leaf node has a pointer to the next leaf node. This is also has a pointer to the next leaf node. Yes, this is also true because we are having the leaf nodes are joined with the help of links. So the correct option is B. What is the worst case time complexity of inserting n square elements into an AVL tree with n elements initially? Initially, the AVL tree will have n elements, and now we are inserting n square elements. So what will be the complexity? So complexity will become theta of n square log n. The explanation of that is given to us. Find the position where to insert, and after insertion, to satisfy AVL property, we need to perform rotations. So step 1 will take log n time and step 2 will take log n time. So log n plus log n will give you 2 log n. So the complexity is O of log n. Now we have to insert n square elements, so it will become n square log n. The pre-order traversal of a binary search tree is given. Which one of the following is the post-order traversal of the tree? So what we have to do here is we have to construct the tree using the pre-order and the post-order. Now we have to try it with option A, then we have to try it with option B, then C, then D. After trying all the options, whichever is the correct tree will give you the traversal in pre as well as post order, and that order we have to follow. So the correct option is A. So here you can see, first of all we have to draw the tree. So from pre order we have concluded that 15 is the root node. So here you can see we have inserted 15. In this way we have to construct the whole tree, then we have to traverse the tree in post order, and then we have to compare it with the options which are given to us, and it is matching with option A. So the correct option is option A. Let T be a binary search tree with 15 nodes. The minimum and maximum possible heights of T are, so a binary search tree with 15 nodes with the minimum and maximum possible heights. So again, for this we have to draw the tree with 15 nodes. So first what we will do is the minimum height we have to find. So in this we have to balance the tree properly. So after balancing the tree properly, the height we'll get is 3, and if the tree is either left skewed or right skewed, then we'll get the maximum height. So that after drawing the tree left skewed or right skewed, the height will be 14. So the correct option is B, that is 3 and 14. So here in tree data structure, mostly the problems which are coming is first we have to construct the tree and then only we can give the answers. So in this way we have to solve the problems. uh, that's it. This much is there in today's lecture. Thank you, all of you.